Hi everyone, I hope you're okay. This is video number 5 from the promised series of answering acids and base questions. Okay, we are told that hydrogen carbonate ions react with water according to the following balanced equation. Okay, uh, this is the hydrogen carbonate ion reacting with water to form carbonic acid and OH minus ions. Okay. Define an acid according to the Lorentz-Bronsted theory. According to Lorentz-Bronsted, an acid is a substance that ionizes in a solution to donate a proton. Okay. Write down the formula of two acids in the equation above. Okay. Let's forward on the forward reaction first, guys. Now, HCO3 minus will later become H2CO3. That means HCO3 has accepted a proton for it to become a carbonic acid. So this guy is a base because it accepted a proton. Are we together? But let's look at the water molecules. H2O became OH minus. That means it became OH minus by giving away a proton. So that means H2O is an acid. Now let's focus on the reverse reaction. H2CO3 will become HCO3 minus. H2CO3 will become HCO3 minus by giving away a proton, which simply means that H2CO3 is an acid because it donated a proton. And then the OH minus will become H2O by accepting a proton. So this one is a base. So the two acids in the above reaction, I have H2O and the carbonic acid. Okay, write down the formula of a substance in the reaction above that can act as an ampholyte. The hydrogen carbonate ions can act as an ampholyte. Why? Because it has the ability to to donate a proton or an ability to accept a proton. Are we together? So this guy over here can act as an ampholyte. And then we are told that during an experiment, 0.5 cubic decimeters of a 0.1 mole per cubic decimeters of hydrochloric acid is added to 0.8 decimeters of a sodium hydrogen carbonate solution of concentration of 0.25. The balanced equation for the reaction is as follows. Okay, this is the balanced equation. Okay, we are told to calculate the concentration of the hydroxide ions in the solution on the completion of the reaction. Okay, we are being told that the reaction will reach completion, and since they want us to calculate the amount of hydroxide ions which will be in excess, which simply means that the base in the reaction will be in excess. Are we together? So we can simply use our titration equation to see how much volume of the base was actually used. We can go Ca Va all over Cp Vp is equal to Na over Np. Now, Ca, if I call this substance A and this substance B, the concentration for substance A, it was 0.1 and the volume was 0.5 cubic decimeters. The concentration of substance B, which is my base, 0.25. I don't know how much volume was used. I want to know the Na and Np, guys, please, they do not represent the number of moles of substance A and the number of moles of substance B, but they represent the stoichiometric coefficients, the number in front of substance A and B. So there's just 1 and 1 there. So the only unknown I have here, guys, it's my volume. So I'll simply say 0.1 multiplied by 0.5 is equal to 0.25 multiplied by volume of my base. Therefore, the volume of my base is simply 0.1 multiplied by 0.5 all divided by 0.25. Let's see what you get. 0.1 multiplied by 0.1 multiplied by 0.5 is divided by 0.25. We get 0.2 decimeter cubed. Okay, remember that, guys, we had 0.8 cubic decimeters and we only used 0.2 cubic decimeters to neutralize the acid. Are we together? So it simply means that the volume in excess is simply 0.8 minus 0.2. We'll simply get 0.6 cubic decimeters. And then therefore the number of moles of my base in excess, number of moles in excess is simply concentration multiplied by the excess volume. The concentration of my base is 0.25 multiplied by 0.6. Remember that the excess volume was 0.6, right? So I'll simply say 0.25 multiplied by 0.6. I'll get 0.15. These are the number of moles of my base in excess, right? Let me highlight them in black. These are the number of moles of my base in excess. But since the base is in excess, whenever it ionizes, it will give a higher concentration of hydroxide ions, right? So I'll simply say my base is NaHCO3. Whenever it dissociates in water, it will form Na plus H2CO3 plus OH minus. Are you together? So for me to calculate the number of moles of the hydroxide ions in excess, I can simply say I know that 1 sodium carbonate, or it's sodium bicarbonate, by the way, or you can call it sodium hydrogen carbonate. 1 sodium bicarbonate will give me 1 mole of the hydroxide ions. But now I do not have 1 mole of sodium carbonate. I have 0.15. I want to know how much of the hydroxide ions will I form. Simply cross multiply. Therefore X, which represents the number of moles of the hydroxide ions in the excess solution, it will be 0.15 moles. So therefore, for me to find the concentration, I simply have to say concentration is number of moles over volume. I'm looking for a concentration of the OH minus ions. I know the number of moles is 0.15, and the volume, remember that both the acid and the base were mixed together, right? So the total volume, it will be 0.8 plus 0.5. So my answer is 0.15 multiplied by 0.8 plus 0.5. I'll simply get 0.112 moles per cubic decimeters. Simply get 0.12 moles per cubic decimeter. So the concentration of my hydroxide ions in the final solution is 0.12 moles per cubic decimeter. Okay, the final question, they want us to calculate the pH of the solution on completion of the reaction. The pH will be determined by the concentration of hydronium ions, right? But right now we have the concentration of the hydroxide ions. There are two ways to do this thing. We can either find the pOH and then find the pH, or use the constant ionization of water to find the concentration of the hydronium ions and then calculate the pH of the solution. It's one and the same thing. So let's find pOH since of the concentration of the OH ions. pOH is equal to negative log of the concentration of the OH ions. I know the concentration is 0.12. So what do I get? Negative log of 0.12. I'll simply get 0.92 as my pOH, right? But remember that whenever I add pH plus pOH, I always get 14. So my pH plus 0.92, so therefore the pH will be 14 minus 0.92. 14 minus 0.92. What do I get? I simply get 13.08 as my pH. If I wanted to go to use the constant ionization of water, I would have said the concentration of the OH minus multiplied by the concentration of the H3O plus is always equal to 10 to the power negative 14. 10 to the power negative 14, right? I do know that this guy is 0.2, so I can easily find the concentration of the OH minus. So the concentration of the hydronium ion is 10 to the power negative 14 divided by 0.2. And then what do I get? 10 to the power negative 14 divided by 0.12. It's 12. Remember that, guys, no? Just to refrain from rounding off, I get 8.33. The 3's are recurring, multiplied by 10 to the negative 14. This is in moles per cubic decimeter, right? So therefore the pH of my solution is negative log of the concentration of the H3O plus, negative log of 8.333 times 10 to the negative 14. What do I get? Negative log of the answer. I simply get 13.08 as well. So it's up to you guys, which one do you prefer? I strongly believe that the pOH route, guys, is much more cleaner. That's the one I prefer the most. But if you want the other one, kudos. This is the end of the 5th video, guys. The 6th video is coming right away.